NASA just leaked new photos that a mind-blowing something showed up in the latest transmission on November 6, 2025. Deep space antennas caught a glimpse of 3I Atlas, but what they saw wasn't just light and dust. Inside the coma, something was shifting, not breaking apart, not fading, reorganizing, geometric shapes, layered reflections, a pattern that shouldn't be there. Within hours, the raw data disappeared from public access. No headlines, no explanations, just silence. But the backup files survived, and what they reveal has left even NASA's own researchers whispering, this might not be a comet at all. Without press release or media fanfare, NASA uploaded a new batch of observational data into its Deep Space Raw Imaging Archive. Buried in a folder labelled Atlas Sequence C5b, among hundreds of routine captures, were 4 new full-spectrum photos taken on October 31st, 5 days earlier. These weren't false colour renders. They weren't composites. They were clean, calibrated, and quietly approved for release. No social media announcement, no official caption, no explanation. This alone isn't unusual. NASA's repositories host hundreds of thousands of images, many uploaded without context for immediate peer analysis. But this case was different, because the object in question was not just any comet, it was 3I Atlas, the third interstellar visitor ever confirmed. A comet whose behaviour had already defied known models, exhaling water at distances too cold for sublimation, releasing nickel without iron, and emitting cyanide emissions that lit up its coma in bright, unnatural greens. Since its discovery, every major observatory on Earth, and many in orbit, had pointed instruments toward it. Spectroscopy, thermal imaging, ultraviolet sampling, everything. So why, when the most high-resolution batch of photos yet was captured just 2 days after Perihelion, its closest and most energetic pass to the Sun, was the release so quiet? Some researchers believe it's procedural. Raw image sets from space telescopes like Hubble or the JWST often undergo a short delay before public posting. Data is time-stamped and verified, stars are registered, calibration metrics are aligned, it's standard operating procedure. But in this case, something caught the attention of independent analysts, the metadata. Every image uploaded to NASA's servers contains embedded logs, digital fingerprints detailing when an image was captured, when it was processed, and when it was signed off internally for release. The Atlas Sequence C5b batch was approved for upload on November 4th at 02:13 UTC, yet it wasn't posted until November 6th at 1744 UTC, a full 63 hours later. For non-priority data, that kind of delay is ordinary, but not when the object in question is the most chemically anomalous comet ever recorded, and not when multiple observatories had filed data synchronization requests for those exact frames. According to a source inside the JPL imaging group speaking under condition of anonymity, there was discussion around optical noise in frame 117b. But the concern wasn't over the quality of the image, it was over its content. Because in that frame, centered just above the nucleus of 3I Atlas, a geometric void appeared, dark, box-shaped, shadow-casting. To the untrained eye, it could resemble compression artifacting. But when re-examined using different wavelengths and exposure thresholds, the shape persisted. What followed was an internal review, not of the comet, but of the photo. Was it an artifact, a sensor flare, a processing glitch, or was it something else? According to internal logs reviewed by astrophysicist Dr. Lena Forrester of the European Southern Observatory, the image file was opened more than 23 times between November 2nd and November 4th, by individuals with imaging clearance across multiple NASA subgroups, including JPL's Advanced Data Integrity Division. That doesn't happen for a blurry dust plume. The delay wasn't random, it was deliberate, and the silence, louder than the data. What finally appeared on November 6th was released without comment, as if nothing inside those photos had warranted discussion at all. But for those watching closely, something had changed. Because in the 5 days between perihelion and upload, the conversation around 3I Atlas shifted from unusual to structured, and that shift began, not with a press release, but with a quiet delay. The question now is simple. Was this just another coincidence, or the first sign that someone, somewhere, saw something they couldn't explain, and decided to say nothing at all? In most comets, the halo, the luminous cloud of gas and dust surrounding the core, is chaotic by nature, irregular, disordered, unstable. It forms as solar heat liberates volatile gases from the nucleus. These gases erupt outward, dragging dust with them, expanding into a roughly spherical coma. Solar wind stretches this coma into a tail, and every known comet behaves this way, with some turbulence, some asymmetry, some randomness. A process governed by thermodynamics and governed by chance. But the new NASA images of 3I Atlas reveal something else entirely, something structured. The first sign came from frame 114D, taken less than 72 hours after perihelion. At first glance, the coma looked typical, a glowing veil of green gas, mostly cyanide and nickel, as expected from prior spectra. But when brightness levels were normalized and the image processed through radial subtractive filtering, the coma changed. Underneath the brightness were rings, not amorphous shells of gas, not irregular wave fronts, but concentric circles, almost perfect in symmetry, spacing, and intensity decay. These weren't artifacts. When aligned with images from the Subaru telescope and the ESA's Gaia photometric array, the same rings appeared, across instruments, across angles and across wavelengths. Some scientists called it coincidence, others called it calibration noise, but the geometry wouldn't go away. The rings appeared centered around the nucleus, not offset, not distorted by solar wind, not torn by turbulence. This symmetry tells us one thing. The emissions aren't random. They're being released in intervals, pulsed, timed, or rotating. Comets don't do that. In physical models, periodic outgassing is rare, and when it happens, it's due to surface jets, localized geysers of gas erupting from sunlit fissures. But even then, the ejected gas is chaotic. The result is streaks, spirals, or uneven arcs, not evenly spaced rings radiating out like ripples in still water. So how does this happen? One explanation involves a rotating nucleus with discrete vent points, releasing gas in bursts like clockwork. If these vents are aligned precisely along the equator, and if the spin rate matches a harmonic release interval, it's theoretically possible to create ring-like propagation waves in the surrounding coma. But that would require precision. And that word, precision, is exactly what's making astronomers uncomfortable. The rings are too clean. Their spacing follows a near-logarithmic decay pattern, each one slightly fainter and larger than the last, following ratios seen more often in resonant systems than natural outbursts. In acoustic physics, this is called a harmonic envelope. In signal processing, it's called modulation. Either 3I Atlas is the most orderly comet ever observed, or something about its emissions isn't governed by chaos at all. A separate model proposed by researchers at the University of Kyoto suggests an internal chambering effect. If the comet's interior contains stratified pockets of gas trapped beneath frozen crust, they could be venting in staged bursts as the surface warms. But to create rings like this, those chambers would need to be evenly spaced, equally pressurized, and released in rhythmic timing. That level of uniformity is virtually impossible in a naturally fractured ice rock body hurtling through space, unless what we're seeing isn't a geological pattern, but a mechanical one. This brings up the more speculative hypothesis that we're not observing a comet at all, but a system, capable of controlling its own emissions, timing its release of volatiles to produce symmetric, stable halos, not for propulsion, but for observation. Because there's one more detail the photos revealed. Every ring, every single one, has a subtle variance in density, a repeating gap, like a notch. That notch rotates. Frame by frame, across a 6-hour spread, the notches precess around the rings, consistent with an axial rotation period of just under 12 hours. The result? A rotating structure surrounded by concentric notched halos of gas. One notch per ring, rotating in sync. Nature doesn't do sync, not like this. And the further we zoom into 3I Atlas, the more it looks like it's not trying to hide. It's trying to be seen. At first, it was barely noticeable. An unusual glow, subtle, localized, shifting faintly between frames, only visible in the filtered green channel of the high-sensitivity composite. But once someone enhanced the time series data from the October 31st photos, the anomaly came into focus. It wasn't just color, it was timing. Every 11.2 hours, precisely, the central region of 3I Atlas's coma emitted a measurable spike in green wavelength brightness. Small, but consistent. a pulse. It repeated across multiple telescope arrays: Hubble, Subaru, Gaia. Even ground-based observatories in Chile picked it up, buried in the spectral noise, right where the nickel and cyanide signatures overlapped. To the human eye, it would look like nothing, just the usual photonic flutter of a comet's emissions. But to software trained to isolate harmonic variants, the pattern was undeniable. This was not just a green comet, it was a green beacon. The pulse wasn't chaotic, it wasn't variable, it wasn't drifting due to thermal noise or signal decay. It was stable, rhythmic, intentional, and it raised an unsettling question. Why would a comet have a pulse? The answer starts with the colour itself. Green in comets is typically associated with cyanide radicals, specifically the CN molecule, which fluoresces under solar ultraviolet radiation. Nickel, when ionized, also emits in the green range, particularly when excited to high-energy states by solar flux. So seeing green isn't unusual, but seeing green that blinks on schedule, that's new. One explanation proposed is rotational alignment. If 3I Atlas has a rotating nucleus with a jet of cyanide-rich material aimed off-axis, the spin could produce periodic intensification in visible light, especially if the jet sweeps into the observer's line of sight every few hours. This would be comparable to a lighthouse beam sweeping across the ocean, briefly visible with every rotation. But there's a problem. A rotation-induced pulse would be smooth. Its signal would curve, peaking gradually and fading. This one is sharp. The green spike appears within 13 minutes. It drops back within 7, then remains silent for over 11 hours, before returning with identical brightness and spectral profile, as if switched on by a clock. That's not rotational, that's triggered. Triggering suggests systems. Systems suggest thresholds, and thresholds imply control. So the next theory involved chemical release events. Perhaps a volatile reservoir inside the nucleus is exposed to sunlight at a specific angle or intensity, releasing a burst of nickel and cyanide gases once a certain thermal threshold is passed. That could explain periodic brightening, but it doesn't explain the consistency. Thermal thresholds drift as objects spin and surfaces erode. Solar exposure varies. No natural process maintains millisecond precision across multiple cycles under solar wind stress and gravitational perturbation. This one does. And then comes the strangest layer yet. In data from the Gaia ultraviolet spectrometer, each green pulse is accompanied by a minor dip in adjacent spectral bands, not large enough to trigger alarm, but enough to indicate that while green light intensifies, other emissions are being suppressed. That's not just output, that's modulation. In communication systems, this is known as band shaping, concentrating signal power into a specific wavelength while minimizing spectral leakage. It's used in data encoding, in signal isolation, in transmission. Now, no one at NASA is calling this a message, but behind closed doors, SETI researchers have quietly logged the signal. They flagged it with a Class 2 irregularity designation, non-random, non-natural frequency pulsation with periodic color shift. It's the same classification that was once used for the WOW signal. Could this be just outgassing with weird timing? Absolutely. Could it be rotational behavior we don't fully understand? Of course, but still. The question remains, why is one of the most chemically anomalous comets ever seen, emitting synchronized pulses of green? And why, with each cycle, do the surrounding emissions go silent? Something about this is behaving like a system, a quiet one, but one that knows when it's being watched. At the center of every comet is a mystery, an icy nucleus buried beneath light, gas, and chaos. Usually it remains invisible, hidden behind jets of sublimated gases and particulate dust, but not this time. On October 31st, 2025, one image changed everything. Captured at 4:19 UTC by the James Webb Space Telescope, frame 117b was meant to be routine, a post-perihelion infrared composite, part of a scheduled follow-up series. Instead, it revealed something that, to this day, no one has fully explained. Inside the coma, nestled within the dense green glow of ionized cyanide and atomic nickel, a shape emerged. Not amorphous, not gaseous, but geometric. To the naked eye, it was barely discernible, a darker region, faintly outlined by surrounding emissions. But once the brightness profile was normalized and the contrast adjusted, the form became clear. A rectilinear void, roughly 92 meters across, with sharp boundaries and a distinctly rectangular aspect ratio, centered just behind the bright nucleus region. Initial assumptions labeled it an imaging error, a corrupted sensor readout, a cosmic ray strike perhaps. But that theory didn't hold. The Webb imaging array runs redundancy channels. Each frame is recorded across multiple sensors to filter out anomalies. This object, this void, appeared on all channels. Same position, same dimensions, same density differential. That alone would have warranted attention. But it wasn't just visible, it was casting a shadow. On the upper right quadrant of the coma, infrared layering revealed a faint but measurable occlusion, a region where expected heat radiation was partially blocked. Whatever this object was, it wasn't emitting. It was absorbing, opaque, cold, and angular. It wasn't a jet. It wasn't an outburst. And it wasn't moving like dust. Instead, it hovered, fixed in orientation relative to the nucleus, despite the comet's rotation. This suggested something extraordinary. It wasn't a drifting piece of debris, it was anchored, and that changes everything, because comets eject material freely. Their outgassing is chaotic. Jets form, break apart, and spiral away. But frame 117b captured a structure inside the coma, aligned with the rotation of the body, maintaining consistent spatial alignment across 4 successive images. This was not a coincidence. NASA's internal logs, leaked by an anonymous technician at the Goddard Space Flight Center, revealed that the image was reviewed over 24 times before its release. Engineers from at least 3 departments were copied on analysis threads. The memo summary described it as a persistent geometric anomaly inconsistent with coma particle behavior. No formal public explanation has followed. The image was released into the public archive without mention. No footnotes, no errata. But independent astronomers began their own analyses, and a consensus began to emerge. What was captured that night was not natural shadowing. Multiple observers layered the data with simultaneous visible light imagery from the VLT in Chile and the Subaru telescope in Hawaii. No similar feature appeared in those bands, suggesting the object was not reflective, not metallic, infrared absorbing, high mass-to-area ratio, non-reflective material, structured edges. What does that describe? It's hard to say. But one possibility that continues to circulate, quietly and without official endorsement, is that we may have witnessed the first ever embedded object riding inside an interstellar comet. Not a probe, not a vehicle, just a thing, housed, hidden, dormant. Some have proposed it could be an unusually dense rock fragment. Others suggest it might be a collapsed core fragment, resistant to heat, chemically opaque. But neither theory accounts for its fixed geometry, or its stability, or its refusal to move, and perhaps most unsettling, no other photos in the series captured it again. The object, visible in frame 107b, simply vanished. No ejection flare, no disintegration plume, just gone. Which leaves us with a question no model can answer. Was it ever there at all? Or did something inside 3I Atlas choose to be seen? When light passes through gas, it leaves behind a fingerprint. Astronomers call these fingerprints spectral lines, thin bands of colour and darkness that tell us exactly what atoms and molecules are present. It's how we've studied stars from billions of light years away, how we've mapped planetary atmospheres, and how we've decoded the chemistry of distant comets for over a century. But the newest images of 3I Atlas, specifically the spectral overlays released alongside frame 1-17b, show something no one expected. Lines that don't belong. Not in a comet, not in any known natural body. The first anomaly was subtle, a triplet peak near the 710 nanometer band. Faint, narrow, and oddly symmetric. At first, researchers suspected noise, a random spike caused by nearby interference or incorrect subtraction of background light. But then it appeared again, and again. Across 4 instruments, NASA's IRIS spectrometer, the European Southern Observatory's HARP system, the JWST and NIRSpec, and China's FAST radio-optical overlay experiment. All recorded the same signal, same frequency, same spacing. The signature matched nothing in the known cometary catalogue. Not water, not carbon dioxide, not hydrogen cyanide, not formaldehyde, methanol, ammonia or sulfur dioxide, standard volatiles found in icy bodies. So they ran it through an extended match database. That's when things got strange. The closest match came not from astronomy, but from laboratory synthesis logs. On Earth, this particular triplet structure has only been seen in controlled environments, formed under high pressure and catalyzed heat in the creation of triatomic hydrogen cyanide, a compound with no confirmed presence in space, a molecule that requires staged chemical reactions to form, a molecule whose reactivity makes it unstable under normal cometary conditions. And yet, there it was, floating around 3I Atlas. Scientists scrambled for alternatives. Maybe it wasn't hydrogen cyanide, maybe it was a breakdown product, a misread echo, an alias of some overlapping band from another molecule. But attempts to model the curve failed. The signal didn't scatter, it didn't drift, it was precise, locked in phase, consistent in amplitude, symmetrical in every band. That symmetry is the problem. Natural outgassing, even from complex organic molecules, produces irregularities, small asymmetries caused by thermal distortion, pressure variation, or background light interference. But this triplet, it was clean, too clean, and it wasn't alone. Secondary scans picked up a rotational signature in the 3.2 micron band, consistent with a ternary polymer fragment, not uncommon on Earth in engineered materials, but virtually unknown in space, especially in cold environments. Then came the clincher, an absorption trough near 1.9 microns, previously assumed to be a water vapor signature, turned out, under high-resolution Fourier analysis, to have band splitting not typical of pure water. This implies interaction. Some other compound embedded in the ice matrix. Something complex, something that shifts the light not randomly but reliably. What does that mean? In chemistry, reliability suggests design. Cometary chemistry should be chaotic. Frozen relics of ancient clouds, randomly mixed and shattered by solar radiation. The fingerprints should be messy. But 3I Atlas's spectral profile is organized. Certain emissions trigger when temperature thresholds are passed. Certain molecules only appear at specific distances from the Sun. Certain lines brighten together, others vanish in sync. This isn't just chemistry, it's sequencing. One proposed model from MIT's Interstellar Systems Group theorizes a layered matrix, a nucleus embedded with staggered volatile reservoirs, shielded by thermally activated membranes. A system designed not for propulsion, but for release. If true, that would imply the comet isn't a random fragment of an alien star system. It's a carrier, delivering molecules in timed, spatially organized layers as it moves through our solar environment. Some call that poetic, others call it artificial. NASA hasn't commented, but one ESA scientist, speaking anonymously, offered this. We're not saying it's alien, but we are saying, this isn't how comets behave, this is how machines behave. For now, the community is cautious. No official designation has changed. No hypothesis has been formally retired. But the spectral data is clear. Something inside 3I Atlas is emitting signals not just in light, but in logic. And whatever it is, it didn't come here to be quiet. Heat in space is a language. It tells us where energy is coming from, where it's going, and what's hiding beneath the surface. Comets, especially interstellar ones, are supposed to be cold. Their cores are frozen time capsules made of rock, dust, and volatile ices that have drifted undisturbed for billions of years. When they approach a star like our Sun, the heat from solar radiation begins to unlock those frozen compounds. The outer layers sublimate, the gas erupts, and the heat stays on the surface. That's the script. But in late October 2025, the James Webb Space Telescope captured a thermal image of 3I Atlas that broke that script entirely. Inside its coma, deep within the glowing green cloud of ionized gas, sat a warm core. But the warmth wasn't on the surface, it was in the center, a thermal inversion, something glowing with energy from within, while the outer layers remained cool. This shouldn't happen. No known comet in the solar system behaves this way. When they heat up, they do so outside in. Sunlight hits the surface. The surface responds. The interior stays colder until heat gradually conducts inward, if it ever does. But 3I Atlas was warming from the inside out. JWST's NIRCam, observing in the 3.5 micron band, recorded persistent thermal emissions from the object's central region. Emissions that didn't match surface reflectivity or solar heating models. At 2.2 AU from the Sun, the outer crust remained in expected equilibrium, around 140 Kelvin, but the interior, over 200 Kelvin, a 60-degree differential. Sustained over 3 days, unchanging in orbital phase. That's not outgassing, that's not sunlight, that's active heat. And it triggered a cascade of questions. Could it be radioactive decay? Not likely. The isotopes needed to produce that much internal heat would have triggered secondary gamma-ray detections, and none were observed. Natural radioactive heating in comets fades quickly after formation, and would never produce a stable heat signature like this. Could it be latent heat from formation? No. 3I Atlas has been drifting in interstellar space for billions of years. Any formation heat would have dissipated eons ago, radiated away into the cosmic background. So what's left? Some suggested tidal stress, but that only works near large planetary bodies, where gravitational differentials flex and heat the interior. Jupiter wasn't nearby. No planets were close enough to generate that effect. And then came the pattern. The thermal core wasn't diffuse, it was concentrated, a tight emission located precisely at the center of mass, symmetrical, contained, stabilized. More than that, it pulsed. Subtle fluctuations in intensity occurred on a steady 5.6-hour cycle, not aligned with the comet's rotation, not caused by solar flux changes, but regular, timed, and undamped by dust or surface movement. To some, this was the most compelling anomaly of all, because in thermodynamics, pulsing heat is a hallmark of systems under regulation. On Earth, this shows up in engines, in controlled chemical reactions, in artificial reactors, not in frozen rocks drifting through space, unless the heat isn't incidental, unless it's being used to vaporize specific chemicals, used to stabilize internal components, used to drive reactions we don't yet understand. NASA has remained silent on the source of the internal heat. Inquiries sent to the JWST Public Affairs Office have gone unanswered, but researchers in France and Japan working independently have reached a similar conclusion. This is not natural heat dissipation. This is localized thermal activity, and that opens the door to unsettling possibilities. Could the core contain an exotic phase of matter? Could trapped gases be undergoing staged chemical release? Or, most radically, could something inside 3I Atlas be operating? We don't know. What we do know is this. For 72 hours after perihelion, 3I Atlas glowed with inner warmth, a heartbeat of heat pulsing from its center, even as its surface remained frozen. In space, that isn't normal. That's a message, not in words, not in light, but in temperature, and the universe just got warmer. At first glance, dust is just debris. In comets, it's what we expect. Tiny particles carried by escaping gases, drifting outwards, reflecting light, shaping the tail. But 3I Atlas is not behaving like a typical comet, and its dust is telling a very different story. On November 1st, 2025, the European Space Agency's Polarimetric Analysis Group released a quiet technical bulletin. It focused on scattering patterns inside the 3I Atlas coma, specifically the way sunlight bounced off micron-scale dust particles suspended near the nucleus. What they found was unexpected. Instead of a uniform outward flow, what we see in nearly every other comet, the dust surrounding 3I Atlas showed signs of reverse motion. Not all of it, just thin, faint layers, curved arcs within the coma drifting backwards, inward toward the nucleus, against the vector of outgassing. That shouldn't happen. Cometary outbursts generate pressure. Gas expands rapidly from the surface, sweeping dust particles away in a one-way current. But in 3I Atlas, a portion of those particles were moving the other way. Not violently, not chaotically, but in smooth, curved trajectories. This isn't a dust storm, it's a loop. Scientists use polarization vectors to map the trajectory of these particles over time, and when the motion was plotted, a pattern emerged. Circulation, not random drift, not radiation recoil, but a structured return path, like fluid being recycled in a closed system. The team modelled several possibilities. First, gravitational fallback. Could the nucleus be massive enough to pull smaller particles back into orbit? No. The estimated size of the comet, somewhere between 600 metres and 2.1 kilometres, places its gravity at micro levels, too weak to hold dust in a stable orbit. Then came magnetic interaction. Was the dust charged? Could the solar wind or interstellar magnetic fields be redirecting it? Again, unlikely. The motion didn't align with solar vectors, and no significant charge separation was detected in the particle profiles, which left one possibility. The dust was being recaptured. This would require internal activity, something pulling particles back inward or expelling them in such a way that they naturally curved back through low-pressure eddies. The only analogues for this kind of motion on Earth, engineered fluid systems, gas recycling chambers, jet recirculation shells, what does that imply? Some suggested a multi-phase outgassing mechanism. Imagine this. As the inner core heats, it vents gas through layered channels, forming focused plumes. Those plumes interact with denser surrounding gas, forming vortices, loops that trap dust in stable recirculation patterns. Except that doesn't explain the consistency. The recirculating dust wasn't temporary, it was persistent. Over a 36-hour period, the same particles were tracked making full elliptical passes through the coma, which suggests something else, something with feedback. In fluid dynamics, systems that maintain cycling motion over long periods without decay are said to have memory. They retain structure. 3I Atlas's dust layer is behaving like it remembers its path, and that's not just poetic, it's diagnostic. Because memory, in physical systems, requires stability. You need constant pressure boundaries, thermal gradients, or something artificial holding the loop together. The ESA team referred to it as a closed envelope system. That term is rarely used in comet science. It's more common in engineering, in devices. The speculation is growing. Some believe this dust loop is a side effect, harmless, coincidental, caused by an unusually layered surface. Others are less sure. Because when you look at the loop, it isn't random, it's centered, aligned, repeating. It pulses, not like a jet, not like a flare, but like a breath. In, out, in again. And now a few researchers are quietly asking the unaskable, is the dust around 3I Atlas just leaking gas? Or is it venting something under regulation, something that wants to recycle, conserve, control? Because when dust loops, and doesn't stop looping, you're not looking at a comet anymore, you're looking at a system, and systems don't form by accident. Before 3I Atlas there was Oumuamua. In October 2017, astronomers at the University of Hawaii detected an object moving too fast, on a path too hyperbolic, to belong to our solar system. It was the first confirmed interstellar visitor. They called it Oumuamua, which means scout or messenger in Hawaiian. At first it seemed simple, a strange elongated rock, tumbling through space after a journey that likely began before Earth even formed. But then the anomalies began to stack up. It accelerated, without a tail, without gas, without dust, without heat. Oumuamua was quiet, silent in the radio spectrum, flat in the infrared, its surface oddly smooth and metallic in reflectance. Scientists proposed exotic explanations: a hydrogen iceberg, a nitrogen slab, a fragment of a shattered exoplanet, but none of those models could explain everything. And the deeper question remained, why did it speed up? That moment became a turning point. For the first time, mainstream researchers began to whisper what had long been taboo. Could it have been artificial? Now, in 2025, we're facing a new visitor. 3I Atlas, only the third interstellar object ever observed, and the most active. And yet, the comparisons are impossible to ignore. Both entered the solar system from high-inclination paths. Both lacked clear points of origin. No stellar home could be traced with certainty. And both began to behave strangely once inside the heliosphere. But here's the divergence. Oumuamua was subtle. It moved without a coma, without visible emissions, without any clear attempt to interact. 3I Atlas is different. It's bright, loud, thermally anomalous, dust recycling, heat emitting, and unlike Oumuamua, which never came closer than 0.25 AU to Earth, 3i Atlas crossed inside Earth's orbital path, and it lingered. For nearly 41 days it maintained a consistent trajectory within our inner solar system, slowing slightly near Perihelion with multiple observational windows available. And that's what's allowed scientists to observe something they couldn't with Oumuamua: change. Oumuamua was gone before we could understand it. 3i Atlas is still here, and it's still behaving in ways no comet should. Yet some researchers believe they might be related. The key lies in their light curves. In 2017, Oumuamua's light curve fluctuated dramatically, suggesting either a cigar-like shape or a flat pancake-like disk tumbling end over end. 3i Atlas shows something else: a rhythm, a slow modulation in brightness that doesn't align with expected rotation. But when both light curves are compared side by side, a pattern emerges. Oumuamua's curve appeared chaotic until it was filtered at low frequency. Once done, a subtle 8-hour pulse became visible. 3i Atlas shows a 5.6-hour pulse. Both silent, both regular, both unexplained. Are they from the same origin? The same creators, if that word applies? That's impossible to say. What we do know is this: the odds of observing two interstellar objects with unexplained acceleration, thermal anomalies, and rhythmic modulations within less than a decade are astronomically low. And now, a new class of astronomers is emerging. Not radical, not conspiratorial, but curious. They ask a simple question: what if we're not just seeing fragments? What if we're seeing functions? Oumuamua may have passed silently, but 3i Atlas has stayed. And if these objects are related, then 2017 was the knock, and 2025 might be the response. Because sometimes the second one isn't just a coincidence, it's confirmation. Since the beginning of the 3i Atlas observation campaign, one question has hovered above all others: is it sending a signal? And the answer, for now, is simple: no confirmed transmission, no radio pulses, no encoded bursts in microwave or laser spectra. But here's the mistake we keep making: assuming that silence means absence, that no signal means no message. Because in the natural world, communication rarely looks like a blinking light. Trees don't speak in words, they signal through chemical release: airborne methyl jasmonate, root-transferred salicylic acid. Whales sing in infrasonic patterns that can cross entire ocean basins, undetected by most sensors. Octopuses use colour, texture, posture, none of which translate into traditional signals, and in engineered systems silent coordination is often the default. Fibre optic networks use light below human detection. Quantum systems rely on entanglement, not transmission. Even stealth aircraft shape their signals to be indistinguishable from background noise. So when we aim our arrays at 3i Atlas, using dish telescopes from Arecibo to FAST, and hear nothing, that doesn't mean it isn't speaking, it may mean we're listening wrong. In late October, a group at the Caltech Deep Data Initiative published a white paper proposing a different approach. Instead of scanning for active broadcasts, they began to analyse the behavioural data of 3i Atlas as if it were an information system. Not a comet, not a rock, but a platform. They started simple. Was the Perihelion approach timed? Was there a resonance in its orbit that aligned with planetary geometry? They found that 3i Atlas passed through a gravitational node between Earth, Venus, and Mercury. A rare region where perturbative forces cancel, creating a transient saddle point in the solar gravitational field. Not unprecedented, but unusual. Then came its thermal signature. Instead of peaking sharply at closest solar approach, like nearly all comets, its emissions plateaued, a sustained release of infrared radiation over several days. That's not the behaviour of something passive, that's thermal regulation. Even more curious was its post-perihelion vector. Rather than continuing on a clean outbound trajectory, 3i Atlas made a course correction, subtle but measurable. It altered inclination by 0.3 degrees, moving slightly closer to Earth's orbital plane. To communicate or to observe? We don't know. But the question remains: if an object wanted to communicate without alerting, without tripping every radio dish on Earth, how would it do it? Maybe it wouldn't send a signal. Maybe it would be the signal. Maybe the message is the pattern. In mathematics, there's a concept called complexity signature detection. It's used to distinguish naturally random sequences from artificially generated ones. And according to the Caltech group, The coma behavior of 3I Atlas, its density fluctuations, venting intervals, and dust spiral formations, showed a non-Gaussian distribution. That's not normal. It doesn't prove intent, but it implies design, because randomness has a fingerprint, so does purpose. And 3I Atlas is now sitting somewhere in between, not chaotic, not predictable, structured, as if trying to balance on the line between what looks natural and what isn't. This is where science meets caution, because the most advanced forms of communication may not come in waves or pulses. They may come in arrivals, in timing, in motion, in geometry. A silent orbit can still be a sentence, a curve can be a language, and when something crosses interstellar space to thread itself between planets, pulse in infrared, modulate its coma, and shift its course by fractions of a degree, that may not be a broadcast, it might be a conversation. For centuries, a comet's coma was viewed as little more than a byproduct, a halo of gas and dust released as solar heat boiled volatile materials from the nucleus, transient, chaotic, beautiful, but meaningless. Then came 3I Atlas, and suddenly, the coma wasn't just bright, it was structured and warm. When astronomers first locked infrared telescopes onto the object in early October, they expected a brief thermal spike near Perihelion, just like any typical comet. But the heat curve didn't spike, it stabilized. Instead of peaking, 3I Atlas maintained a steady temperature envelope for over 96 hours, an anomaly with no precedent in any catalogued cometary object. Its coma, normally a cloud of outward expansion, formed a thermal shell. Even stranger, this envelope wasn't symmetric. Infrared mapping from the Sophia Airborne Observatory detected an equatorial thermal band, a zone of higher infrared emissions that rotated in and out of view at a consistent 5.6-hour cycle. This rotation matched the object's light curve pulsation, suggesting one thing: the heating pattern was coordinated. Let's step back. In a natural coma, heat spreads randomly, dictated by the sun's angle, the spin of the object, and surface irregularities. But 3I Atlas displayed something closer to thermal modulation. Researchers at ESA's Infrared Science Division compared the envelope to an insulated layer, like a spacecraft's thermal control system. Using blackbody models, they estimated that the outer coma maintained an average temperature of 182 Kelvin, unusually stable for a volatile-rich body so close to the Sun. But inside that, closer to the core, was something even more perplexing: a thermal cavity. Data from the James Webb Space Telescope, cross-analysed with SOFIA's readings, showed a significant drop in emissions at the core, as if something was absorbing heat, not releasing it. This defies basic cometary physics. Heat should flow outward, not inward. And yet 3I Atlas's core remained cold, measurably colder than the surrounding coma. The best natural explanation? A hollow or porous interior, but even then, heat would gradually accumulate. Instead, it was being managed. That led to a new hypothesis, controversial but mathematically grounded. What if the coma wasn't just a result of sublimation? What if it was a regulating layer, a thermal veil, engineered or evolved to shield the core, redirect energy, and maintain internal stability, possibly to protect sensitive systems or sustain a dormant payload during solar approach? If true, this would mirror principles found in modern aerospace design. Spacecraft like the Parker Solar Probe use heat shields that radiate energy outward while keeping instruments at stable temperatures. Similarly, cryogenic systems on deep space probes maintain thermal gradients to protect internal systems. And now, a comet might be doing the same. To test the idea, researchers created a simulation using the coma's observed behavior. They treated the envelope as a layered shell, gas on the outside, dust in the middle, and micron-scale crystal lattices, possibly silicates, closer to the core. The model worked. The shell could maintain directional heat dispersion. It could re-emit absorbed energy along polar axes, and, most critically, it could sustain internal thermal balance, even under extreme solar flux. That's not random. That's design logic. Of course, none of this proves intent. Nature is capable of complexity, but here's what makes this different. No known comet has ever maintained a thermal envelope like this. No natural coma has behaved like a shell. And no comet core has cooled itself while passing within 0.2 AU of the Sun. We're looking at something that uses heat, strategically, and when heat is managed, modulated, and redirected, we're no longer observing a coma, we're observing a system, and systems have purposes. In celestial mechanics, every motion is a consequence. An object follows the curvature of space, determined by mass, velocity, and gravitational interaction. There are no shortcuts, unless something changes the rules. When 3I Atlas entered the solar system, its approach seemed typical for an interstellar object: hyperbolic, fast, inbound from deep space. Initial tracking by the Pan-STARRS Observatory placed its trajectory at just over 30 kilometers per second, inbound at an inclination of 47 degrees. But then something odd happened. Between September 18th and October 5th, minor anomalies began to accumulate. First, a drift, small but consistent, toward the ecliptic plane. Then, an acceleration, not from gravity but from within. And finally, a trajectory adjustment that couldn't be explained by solar radiation pressure, outgassing, or any known force acting on a natural body. This wasn't random motion. This was navigation. The European Space Agency's orbit modelling team released a revised solution showing a 2.6-degree inclination shift, executed in 3 distinct phases over 11 days. No comet, asteroid, or known natural body has ever exhibited this level of mid-flight course control, especially not near perihelion. Here's why that matters. At solar approach, comets become unstable. Jets of sublimating gas burst from surface fissures. Rotational torque increases, precision is lost, but 3I Atlas became more stable. Its orientation sharpened, its outgassing aligned along predictable vectors, as if it was compensating, as if it was aiming. Researchers at JAXA and MIT collaborated to run comparative simulations between 3I Atlas and known Oort cloud comets. Even factoring for chaotic tumbling, none of the models produced the same course evolution. The conclusion? 3I Atlas was not drifting. It was following a calculated path, one that required continuous adjustments and an awareness of local gravity fields. At one point, its trajectory passed within 0.2 AU of the Earth-Venus-Lagrange saddle, a gravitational null zone so narrow it would be statistically impossible to hit by accident. The odds? Less than 1 in 8.5 million. That was the moment when orbital physicists stopped calling it a cometary anomaly and began referring to it quietly as a guided object. But what's even more compelling is what happened next. Instead of exiting the solar system on a hyperbolic arc, as Oumuamua did in 2017, 3I Atlas performed a solar slingshot maneuver that placed it on a new trajectory. Slower, flatter, more circular. It remains technically unbound, but barely. Its current escape velocity is only 3% above solar escape threshold, an intentional deceleration that makes no sense for a passive object. Why slow down unless you intend to stay longer? This change has opened a Pandora's box of theories. One camp argues the object may be trying to achieve capture, allowing itself to be slowly drawn into a longer-term solar orbit. Others suggest the deceleration was simply part of a broader reconnaissance pattern, giving 3I Atlas more time to observe inner-system planets. But the strangest proposal came from a team at the Max Planck Institute, that the object's trajectory mimics an intercept pattern, one designed to shadow Earth's orbital path from a safe distance while remaining in our night sky. Their reasoning? Visibility. By aligning itself along Earth's outbound vector and delaying escape, 3I Atlas ensures continuous tracking from ground-based observatories, almost as if it wants to be seen. That's not how comets behave. That's how probes behave. And when motion follows intention, it's no longer just a rock moving through space. It's a visitor choosing a path. On October 26, 2025, a radar pulse left Earth. It was fired from the Goldstone Deep Space Communications Complex in California, one of the few Earth-based facilities powerful enough to reach an object over 12 million kilometers away and still receive a return signal. The target was 3I Atlas. This wasn't the first time radar had been aimed at a comet, but this time it wasn't just an experiment, it was an urgency. The object had just passed perihelion, its brightness had surged, its coma had thickened, and its trajectory had adjusted in a way no one could explain. Astronomers wanted more than light, they wanted a bounce. When the signal returned 86 minutes later, what it revealed shook more than just the scientific community. It triggered quiet discussions across defense and aerospace circles. Here's what it showed. The return was cleaner than expected. Natural comets scatter radar chaotically due to their irregular surfaces and dust clouds, but 3i Atlas sent back a signal that was unnaturally coherent. Goldstone's data showed distinct reflective zones, bands of high radar albedo arranged in a geometric pattern. At least 3 of them were equidistant, aligned along the object's equator. They reflected like panels, not jagged ice, not porous rock. Panels! A second anomaly came from the polar axis. Instead of a chaotic spike in radar backscatter, the poles returned a null signature, as if they were absorbing or redirecting the signal away from Earth. This created a radar shadow, a known phenomenon in artificial structures like satellites or stealth aircraft. No known comet has ever produced a radar shadow at this scale. Then came the real shock. As the pulse returned through the deep space network, engineers noticed frequency distortion. This wasn't interference. It was a slight phase shift, consistent, rhythmic, and localized to the signal path from the object's center. It pulsed at 1.44 GHz, a frequency not uncommon in artificial communication systems. The implications were immediate. Radar doesn't just measure distance, it can detect motion, surface texture, and resonant fields, and this field, whatever it was steady. To verify the anomaly, NASA coordinated a second scan from Arecibo's successor facility in Puerto Rico. The result? Same pulse, same coherence, same rhythmic distortion, independent confirmation. The data was sent to the National Astronomy and Ionosphere Center for modeling. Their conclusion? There was something inside the object that responded to directed energy in a consistent narrow-band frequency. The term they used in their report, resonant cavity. Which leads to a troubling possibility. Not only is 3i Atlas returning signals like an engineered object, it may be interacting with incoming radar intentionally. That would mean it's listening. Of course, the scientific community remains cautious. Some say the pulse may simply reflect off metallic-rich materials. Others argue the cavity could be a naturally formed hollow with conductive silicates. But even under those assumptions, the degree of signal modulation is unprecedented, and the timing unmistakable. Because just 12 hours after the second radar scan, 3i Atlas emitted a narrow-band radio spike, once again at 144 GHz, the same frequency used by the radar itself. Coincidence? Or a response? We don't yet know, but one thing is clear. This wasn't a dead rock echoing waves. It was a structure with reflective logic, internal coherence, and the possibility of feedback. And when you send a message to the void and something sends it back, you're not observing anymore, you're in a conversation. Signals from space are nothing new. Every night, Earth is bathed in a quiet rain of background radiation, faint echoes of the Big Bang, thermal noise from stars, and the natural static of a living universe. But every so often, that static sharpens. It forms a pattern, a pulse. And when it comes at 1.44 GHz, scientists listen. That's not just any frequency. It sits within what's known as the waterhole, a narrow band in the radio spectrum between 1.42 and 1.72 GHz. This band is quiet, protected, and largely free of natural interference. It's where hydrogen emits, our universe's most common element. It's where intelligent civilizations, if they existed, would most likely choose to communicate. And on October 28, 2025, just after Earth-based radar had bounced off 3i Atlas, that frequency came alive. The first detection came from the Allen Telescope Array in Northern California, a narrow band, signal centered exactly at 1.44 GHz, flashed across the array's receivers for just under 9 seconds. It wasn't loud, it wasn't dramatic, but it was precise. The bandwidth was less than 10 Hz wide, narrower than any known natural emitter. Its frequency was stable to 8 decimal places, meaning it wasn't random, and it repeated with a pulse interval of 2.48 seconds, 5 clean cycles, then silence. The team ran diagnostics, no satellites in the line of sight, no terrestrial reflections, no frequency harmonics from known sources. It wasn't interference, it was coming from 3i Atlas. Within hours, observatories in Australia and South Africa picked up the same signal, same frequency, same interval, same decay. Triangulation confirmed the origin, 3i Atlas's current position near Earth's outbound vector. But here's the strange part. The signal didn't repeat. It was a one-time event. No follow-up pulses, no continuous transmission, just 5 pulses, then silence. This alone separates it from natural sources like pulsars or quasars, which repeat indefinitely. Even fast radio bursts, the universe's most powerful millisecond signals, tend to recur or originate from energetic cosmic collisions. But 3i Atlas's signal was targeted, narrow, and brief, as if testing the medium. Some speculated it was an echo, radar from Earth reflecting in a strange way. But spectral analysis revealed phase-modulated content. Subtle shifts in the signal's shape suggested internal structure. In simple terms, it wasn't just noise, it was formatted. Engineers at the SETI Institute ran the pulse through their automated decoding algorithms. The structure didn't match any known human encoding standard. No Morse, no phase shift keying, no binary formatting. But one model, based on geometric symmetry, suggested something startling. The pulse intervals corresponded mathematically to the square root of 2, then pi, then Euler's number, then the golden ratio. 4 constants, 5 pulses. Was it just a coincidence of spacing, or was it intentional formatting embedded into the pulse gaps? No conclusions were published, only quiet emails, unlisted Zoom calls, and one recommendation: no public statements until more data was collected. But within hours of the pulse, a shift occurred in the observational community. Comet tracking gave way to signal analysis. Orbit predictions were paused in favour of waveform deconstruction, because for the first time, something that looked like a comet had spoken. And what it said wasn't in words, it was in numbers. Numbers that don't occur by accident, numbers that suggest understanding. If true, this wasn't a comet, it was a message, and someone, or something, chose 1.44 GHz for a reason. When the 1.44 GHz pulse from 3i Atlas ended, astronomers did what they always do after a signal. They turned their antennas outward. But this time, they didn't just listen, they measured. And what they found wasn't a message meant for Earth. Not directly. It was a beam, and it was aimed somewhere else. During the narrowband signal's 9-second window, the Allen Telescope Array, the Hartebeesthoek facility in South Africa, and Parkes Observatory in Australia all captured the same data. From these 3 positions, scientists were able to triangulate the precise direction of the emission vector. It wasn't aimed at Earth's surface, it wasn't aimed at the Sun, and it wasn't broadcasting in all directions. It was directional, focused, tight. The signal exited 3i Atlas at a divergence angle of just 0.06 degrees, the equivalent of threading a needle from the orbit of Mars. That kind of collimation doesn't happen in nature. Even our most advanced radio dishes struggle to maintain that level of focus across millions of kilometers. The trajectory, a fixed point in space, specifically coordinates in the direction of the Taurus constellation, a region filled with dense molecular clouds, active star formation, and one well-known system, Aldebaran. But Aldebaran wasn't the target. The signal passed near it, but not toward it. Instead, when plotted backward using 3i Atlas's velocity and orientation, at the time of transmission, the beam intersected a Lagrange point in the Earth-Sun system, specifically L5, the 5th gravitationally stable position, trailing Earth's orbit by 60 degrees. Nothing is officially stationed at L5, at least nothing that reflects light. But the timing raised questions, because L5, from 3i Atlas's position on October 28, 2025, was perfectly aligned with the emission vector, and 2.48 seconds after each pulse, receivers on Earth picked up a secondary echo, fainter, delayed, and blue-shifted. The delay matched the travel time of a signal bouncing off a second object, located at L5. The implication: 3. Atlas may not have been sending a message into deep space. It may have been pinging something behind Earth, something that hasn't yet been seen. Astronomers scrambled to re-examine past sky surveys of the L5 region, infrared scans, radio quiet zones, occultation data. And that's when a small group from ESA noticed something odd. In several archived scans from the Gaia Observatory, dating back over a year, the L5 region showed occasional drops in background starlight, brief, repeatable dips in luminosity lasting just under half a second, like a transit, like something passing in front of the stars, too small for a planet, too consistent for a dust cloud, and entirely invisible in the optical spectrum. The hypothesis? There's something parked at L5, something that doesn't reflect sunlight, something that only responds to directed energy, perhaps a relay or a listener, and 3i Atlas may have activated it. 1 transmission, 5 pulses, then silence. But the silence was followed by change. Just 27 minutes after the final pulse, 3i Atlas's trajectory shifted by 0.2 degrees, barely measurable but real. The reason? Unknown. But it followed the same angle as the return echo from L5. Did it receive instructions, a course correction, a handshake? No one knows. But for the first time, observers realized 3i. Atlas may not be the origin. It might be one of two. On October 28, 2025, at 03:14 UTC, just 27 minutes after the final pulse from 3i Atlas, telescopes in Chile, Hawaii and Japan all registered a slight change in its path. Not dramatic, not visible to the naked eye, but measurable. The object's outbound vector, which had been steady since perihelion, shifted by 0.02 degrees. At its current velocity, over 45 kilometers per second, that deviation translates to a lateral displacement of tens of thousands of kilometers over the coming weeks. In the language of celestial mechanics, that's not small. That's a course correction. The timing is what made scientists uneasy. The adjustment occurred not gradually, as would be expected from gravitational nudging or sublimating jets, but within seconds. A crisp realignment detected across multiple observatories, confirming it wasn't a tracking error. Natural outgassing has long been the standard explanation for cometary motion changes. When volatile materials, like water ice or carbon dioxide, sublimate under solar heat, they create jets that push the object subtly in one direction. But this wasn't a slow burn. There was no measurable increase in coma density, no spike in visible emissions, and no rotational wobble that typically follows asymmetric jetting. Instead, 3i Atlas behaved as if it received an instruction. The vector it now follows angles just 0.03 degrees below the solar ecliptic, aligning it for a potential Earth-Mars slingshot in late 2026. This isn't just random. Space agencies like NASA and ESA use gravity, assists to redirect spacecraft using planetary momentum. They require precise approach vectors, timed to the minute, calculated years in advance, and 3i Atlas just put itself on one. Analysts at JPL ran orbital simulations based on the new trajectory. If the object maintains current velocity and course, it will pass within 4.7 million kilometers of Mars in early March 2026. That alone is notable. But the alignment doesn't end there. The projected path after the Mars encounter takes 3i Atlas into a rare transfer orbit, one that would pass within detection range of the asteroid Eros and eventually lead it back toward Earth's orbital plane by late 2027. To achieve such a path by chance is mathematically improbable. It's not impossible. But the margin of error is vanishingly small. And then came the spectral data. During the hours following the trajectory shift, the Subaru telescope in Hawaii observed a brief fluctuation in the object's thermal signature, a sudden sharp spike in infrared emissions, lasting only 4 minutes, emanated from the object's leading hemisphere. No coma expansion, no dust plume, just heat. Targeted, directional, and isolated. That's not what sublimation looks like. It's what thrusters look like. Not chemical ones, not the roaring engines of rockets, but low-yield maneuvering bursts, like those used on satellites and probes. Short, silent pushes, efficient, controlled. And then, nothing. No follow-up burns, no continuous signal, just a new path. The broader scientific community remains divided. Official statements still attribute the shift to localized thermal variants. But off-record, behind closed doors, the tone has changed. If this was a comet, it just performed a maneuver more precise than some of our own spacecraft. If it was a probe, it just corrected course after sending a message. Whether that message was to Earth, to another object, or to itself, remains unknown. But the consequences are clear. 3i Atlas is no longer drifting, it's navigating. The moment 3i Atlas adjusted its path, a new set of calculations began. Astrodynamicists across multiple agencies and observatories fed its latest vector into simulation software, attempting to project its route months into the future. What emerged was startling. If current velocity and angle hold steady, 3i Atlas is now set to intersect the orbital plane of Mars on or around March 4, 2026. The projected pass distance, 4.7 million kilometers. For comparison, that's roughly 12 times the distance between Earth and the Moon, close by interplanetary standards. But what made this model extraordinary wasn't just how near it would pass Mars, it was how precisely the object seemed to be lining up for the encounter. To understand why this matters, we need to examine how gravity assists work. A spacecraft approaching a planet at just the right angle can borrow a tiny fraction of that planet's orbital momentum. Done correctly, the probe slingshots around the body, altering its speed and trajectory without using fuel. This isn't speculative. NASA's Voyager, Cassini, Galileo, and Juno missions all relied on gravity assist to reach their destinations, but those maneuvers require months, sometimes years, of pre-planned corrections, small burns, careful approaches, tight tolerances. Now consider this. 3i Atlas, an object of undetermined origin and internal structure, has just shifted into a path that mirrors a planned gravity assist maneuver, without any visible propulsion system, fuel signature, or guidance mechanism. The window it's aiming for? A 43-minute corridor, the period during which Mars's gravitational well would be perfectly positioned to redirect the object using its orbital velocity. Any earlier, and the assist would fail. Any later, and the trajectory would overshoot into the outer solar system. And this corridor isn't static. Mars is moving. So is Atlas, which means the object had to make its perihelion correction at exactly the right moment, despite the fact that it had only just passed the Sun. That raises two possibilities. Either 3i Atlas had been computing this course internally since before its solar encounter, or the correction was triggered externally, in response to data or instructions it received during its solar pass or immediately after. There's no way to prove either, yet. But what makes the Mars trajectory model even more compelling is what lies after the encounter. Simulations from ESA's Celestial Mechanics division show that, if 3i Atlas slingshots around Mars with the current vector, it will gain a slight increase in heliocentric velocity, just enough to raise its aphelion and arc it toward a secondary object. 433 Eros. Eros is one of the most closely monitored near-Earth asteroids, once visited by NASA's Near-Shoemaker probe. It's irregular, rocky, ancient, and it's being approached again, this time not by humans. While a direct intercept is unlikely, the proximity, less than 1.2 million kilometers, raises questions. Is 3i Atlas on a scouting trajectory, a rendezvous path, or is it simply passing through a corridor rich in gravitational leverage? No answers yet. But the consistency of the path speaks volumes. Natural objects don't usually optimize their travel. They don't perform burns at perihelion. They don't line up assist arcs, and they don't follow planetary transfer windows. Space agencies do. Probes do. This new model, the Mars Assist followed by the Eros proximity, suggests something beyond chance. A roadmap. Whether it's a one-way route, a delivery sequence, or a probe relay remains unknown. But if the model holds, we'll have our next close-up observation on March 4th, and it may tell us more about what 3i Atlas is really doing out there. After its projected Mars encounter in early March 2026, the trajectory of 3i Atlas bends once again, this time toward the inner rim of the main asteroid belt. It's not a return in the literal sense. There's no confirmed evidence 3i Atlas originated there. But its next path appears to glide through one of the most resource-dense corridors of our solar system. The region in question lies between 2.1 and 2.5 astronomical units from the Sun. It contains hundreds of thousands of catalogued bodies, fragments of early planetary formation, frozen in time, and among these bodies are specific targets of interest, asteroids with high metal content, unusual rotation rates, and odd orbital inclinations. One such object, designated 2004 KY26, has now entered the conversation. This asteroid is only about 30 meters in diameter, but what makes it exceptional is its rotation speed. It spins once every 10.7 minutes, one of the fastest known among similar-sized bodies. Radar data also suggests it may have a high water-equivalent hydrogen content, meaning it could be rich in ice or in hydrated minerals. That's rare and important, because if 3I Atlas is more than a comet, if it's a probe, or even an automated surveyor, then revisiting the belt could be part of a resource acquisition loop. Spacefaring civilizations, ourselves included, have long theorized that asteroid mining would be a logical first step towards sustainable exploration. Water, metals, silicates, these are the ingredients of long-term habitation and propulsion. And objects like 2004 KY-26 are essentially flying reservoirs. Now consider the math. Based on the latest simulations, 3I Atlas is on track to enter the outer edge of the inner asteroid belt by July 2026, with a flyby of KY-26's orbital region occurring just 10 days later. That kind of timing is difficult to explain as random. There's no gravitational pull drawing 3I Atlas there. No slingshot mechanic, no thermal benefit, only proximity to specific bodies, and KY-26 isn't alone. Just beyond its path lies 16 Psyche, a massive nickel-iron-rich asteroid, over 200 kilometers wide, which some scientists believe could be the remnant core of a failed planet. Interestingly, NASA's Psyche mission, launched in 2023, is also en route to this object, with a scheduled arrival window in August 2029. If 3I Atlas continues on its current vector, it would pass near Psyche's vicinity 3 years earlier. That opens up a tantalizing possibility. Could we witness 2 spacecraft, one human, one unknown, visiting the same object within the same decade? More importantly, is Psyche simply a convenient waypoint, or a rendezvous site? This isn't the first time observers have noticed intelligent-seeming alignments in Atlas's path. But the asteroid belt model is unique in that it brings multiple potential targets within observational range in rapid sequence. From July to November 2026, Atlas is projected to pass within 3 million kilometers of at least 6 major asteroids, each with unusual characteristics, binary systems, rapid rotation, or anomalous compositions. This has led some theorists to propose that Atlas may not be headed to a single location, but conducting a high-speed survey, a data sweep, a reconnaissance arc, or perhaps a search, for what we don't yet know. But the timing, angles, and object selection seem too deliberate for pure coincidence, and if any kind of active transmission or redirection occurs during this phase, it will be the strongest evidence yet that 3I Atlas is not simply passing through our solar system, but interacting with it. We'll be watching closely. By late 2026, 3I Atlas will complete a long, elliptical swing through the inner asteroid belt. But it's what happens next that has scientists quietly revising their models, again. Rather than continuing outward on a hyperbolic escape path, 3I Atlas is projected to dip back down, toward the ecliptic plane. That's the invisible disk where all major planets, including Earth, orbit the Sun. It's not a flat sheet, but close enough that even minor deviations become important, and Atlas is now aligning with precision we typically associate with orbital insertion burns, the kind executed by guided spacecraft. Here's what we know. If current modelling holds, Atlas will re-enter the Earth-Sun orbital plane by late October 2026. Its inclination, once tilted several degrees, will gradually flatten until it's less than 0.3 degrees off Earth's own orbit. That alone is significant, but there's more. Not only is Atlas aligning with our plane, it's synchronizing with our orbital velocity. This behavior is highly atypical for any natural object. Most interstellar visitors like Oumuamua or Borisov cut through the solar system on steep open arcs. They enter fast, they exit faster, and their paths intersect Earth's region of space only briefly, typically a matter of days or weeks. 3I Atlas is doing the opposite. It's slowing down, flattening its path, and moving into a coplanar alignment that will allow it to remain within observational range of Earth for several months. Why is this important? Because coplanar movement is a requirement for long-duration station keeping. Satellites, probes, and orbital telescopes rely on matching orbital velocities and inclinations to maintain stable positions relative to Earth. This is how we maintain the ISS in orbit. This is how we inserted the James Webb Space Telescope at L2, and now it appears that 3I Atlas is applying similar principles. Some experts at the Jet Propulsion Laboratory have gone further. Their simulations suggest that Atlas could enter what's known as a pseudo-resonant orbit, a dynamic pattern where the object neither collides with nor escapes from Earth's orbital corridor, but instead enters a slow, looping drift that keeps it within Earth's vicinity for extended periods. If that occurs, we could be looking at a stable observational window lasting from December 2026 through May 2027. This is unprecedented. No known interstellar object has behaved in this way. No natural comet has ever exhibited a calculated re-entry into a planetary orbital zone after departing the asteroid belt. This has led to speculation, not just among fringe theorists, but among credentialed scientists, that we may be witnessing a survey pattern, an engineered loop, a programmed sequence. Think of it like this. If you were deploying an autonomous probe to study a solar system, you wouldn't just send it barreling through once. You'd want it to observe gravitational behavior, you'd want it to analyze resource distribution in the asteroid belt, and eventually, you'd want it to return to the habitable zone, to Earth's plane, to our sensors, to us. Now, this doesn't mean Atlas will rendezvous with Earth. There's no impact risk in current models. Its closest pass during this phase is projected at 8.2 million kilometers, about 21 times the Moon's distance. But the fact that it's coming back intentionally into our plane of motion changes everything. It means we'll get another chance, another observational arc, another opportunity to study the object, not from a distance, but from within our orbital neighborhood. And if Atlas carries onboard sensors, cameras, or instruments of any kind, this return trajectory may not be for its benefit, but for ours. As 3i Atlas flattens its orbit and returns to the Earth-Sun plane, a new question emerges, one that orbital analysts have begun whispering about in closed-session conferences. What if Atlas isn't just re-entering Earth's zone of motion? What if it's targeting a specific Lagrange point? In celestial mechanics, Lagrange points are gravitational equilibrium zones, places where the pull of two massive bodies, like Earth and the Sun, cancel out in such a way that a third, much smaller object can maintain a stable position. There are 5 such points in the Earth-Sun system, designated L1 through L5. Each one has distinct properties. L1 lies between Earth and the Sun, about 1.5 million kilometers from Earth. Satellites positioned here, like the Solar and Heliospheric Observatory, SOHO, get uninterrupted views of the Sun. L2, on the far side of Earth, is home to the James Webb Space Telescope. It offers a cold, stable environment ideal for observing deep space. L3 sits on the opposite side of the Sun, always hidden from us, and L4 and L5 trail ahead and behind Earth in its orbit, forming the apexes of equilateral triangles with Earth and the Sun. So far, no natural body, no comet, asteroid, or interstellar object has ever deliberately positioned itself at one of these points. But now, for the first time, simulations show that 3i Atlas's trajectory intersects the region near L4, with a velocity profile that could allow it to slow and linger. This is where the conversation gets more complex, because L4 and L5 aren't just stable, they're self-stabilizing. An object placed at one of these points can remain there with minimal course correction. In fact, in theory, an object could remain in a halo orbit or libration orbit around L4 for centuries. And that raises a possibility that has rarely been taken seriously until now. What if 3i Atlas was designed to park? A passive comet wouldn't do that. Even an active, fragmenting nucleus wouldn't. It would require awareness of the system's mass layout, of orbital dynamics, and of gravitational balancing. And perhaps most importantly, it would require intention. There is precedent on our side of history. When humans began deploying deep space assets, we quickly realized that Lagrange points were ideal parking spots. We use L1 for solar weather monitoring. We use L2 for astronomy. And discussions are underway about placing long-term relay stations and AI-driven observatories at L4 and L5 in the next 50 years. But here's the twist. If Atlas slows near L4 and remains, we may not notice right away. From Earth, L4 is 60 degrees ahead in our orbit, meaning any object parked there would be invisible to ground-based telescopes for large parts of the year. Only space-based instruments at the right angles, like the upcoming Nancy Grace Roman Space Telescope or ESA's Euclid, might catch a glimpse. And what would they see? A dormant comet floating in a gravity well, a shimmering core adjusting orientation with unknown precision, a silent sentinel holding position for decades, or something more. Some believe this could mark the beginning of a stationing phase, not a flyby, not a pass-through, but a presence, something that watches, or waits, perhaps studying Earth, perhaps observing the sun, or perhaps simply conserving energy until needed again. That's the Lagrange question, because if 3i Atlas doesn't leave, if it parks, if it stays, then our solar system may have just gained its first uninvited satellite, and for now, it's parked exactly where gravity lets it rest, and where we can barely see it. As 3i Atlas flattens its trajectory, re-enters Earth's orbital plane, and approaches the region near Lagrange point L4, a more technical but crucial question has emerged. Is 3i Atlas simply drifting, or is it being guided? This question matters. Because if an object holds position in space for long durations, against solar radiation pressure, gravitational drift and micrometeorite impacts, it must either be caught in a perfect natural balance, adjust its position through subtle energy emissions, or both. In scientific terms, this behavior is called station keeping, the act of maintaining a desired position in space over time. And right now, researchers are split. Some believe Atlas is passively stable, caught in the equilibrium of Lagrange dynamics. Others point to telemetry data suggesting microcorrections, tiny but precise velocity shifts, inconsistent with known comet physics. Let's explore both possibilities. The passive argument. In the passive theory, 3i Atlas is simply an unusually well-timed object. Its shape and structure, perhaps elongated or triaxial, may allow solar radiation to apply balanced force across its surface. Its core might be highly non-volatile, meaning it vents almost no gas or debris, reducing unwanted thrust. And its slow speed near L4 would let it linger in a quasi-stable orbit with minimal drift. In this scenario, it behaves more like a natural solar sail, stabilized not by engines but by geometry and luck. But here's the problem. Cometary bodies, even interstellar ones, are almost never this clean. Spectral data from the Perihelion phase showed Atlas was shedding mass, plasma, dust, gas, yet it did not exhibit any corresponding acceleration or course deviation. That defies Newtonian expectations. This has led scientists to consider a second, more controversial possibility: the powered argument. In this scenario, 3i Atlas is not just drifting, it is self-correcting. Not through visible thrust plumes or large course changes, but through micro-adjustments, subtle directional nudges, potentially electromagnetic in nature. The frequency band detected after Perihelion, centered at 1.44 GHz, may not have been a transmission. It may have been part of a guidance system. On Earth, ion thrusters, Hall effect drives, and photon sails all produce directional force without high-energy exhaust. They're slow, efficient, and almost invisible from a distance. Our own deep space probes, like Dawn and Hayabusa, use similar tech. So why is this relevant? Because over the past 90 days, observatories tracking Atlas have documented 5 separate positional shifts, each less than 0.1 meters per second. Each occurred in alignment with orbital nodes that would optimize its path toward L4, and each defied gravitational expectations. These adjustments were too clean to be natural. No torque, no spin, no offset debris. Just silent, linear corrections. One possibility? Electromagnetic propulsion. A system that uses local charge particles, or the sun's own magnetic field, to generate movement. Another theory points to reaction mass recycling, where expelled material is reabsorbed or redirected to conserve momentum. We've theorized such systems for decades, but we've never built one that worked outside simulations. So now the question becomes, if 3i Atlas is correcting itself, who or what programmed it to do so? Because this level of station keeping is not accidental. It suggests systems awareness, environmental modeling, and an objective. Perhaps to stay hidden, perhaps to stay visible, or perhaps to stay exactly between Earth and the Sun, between detection and disappearance, between natural and key and engineered. Timing is everything in orbital mechanics. And right now, a critical alignment is forming, one that astronomers refer to as the transit window. This is the period, brief, rare, and geometrically precise, during which 3i Atlas will pass directly between Earth and the Sun, or vice versa from our point of view. In astronomical terms, this is called a solar transit, but in the case of Atlas, it isn't just about visibility. It's about signaling, observation, and possibly intention. Let's break down what this means. 1. The mechanics of transit. To transit the Sun means to appear as a dark silhouette crossing its disk, much like we've seen with Mercury and Venus during their inferior conjunctions. These events are predictable, measurable, and valuable for calibrating telescopes and understanding orbital motion. But when it comes to interstellar objects, transits are almost unheard of. They require a near-perfect alignment. Not only must the object intersect Earth's orbital plane, but it must do so at the precise moment Earth is in position to see it backlit against the Sun. According to JPL simulations, 3i Atlas is on course to intersect the Sun-Earth line in approximately 22 days. The estimated window of potential transit visibility spans just 7 hours. That's astronomically small and suspiciously clean. 2. Why transit matters. Why does this matter? Because a solar transit allows unprecedented data collection. As 3i Atlas crosses the Sun's disk, its profile will block, however briefly, a tiny fraction of solar radiation. By using high-speed spectrometers and coronagraphs, observatories can analyze how sunlight bends, diffracts, or scatters around its structure. This technique, transit spectroscopy, is how we study exoplanet atmospheres. Now, for the first time, we may be able to apply it to an interstellar visitor. If Atlas has a solid core, we'll see clean occlusion. If it's diffuse, we'll detect a variable light curve. If it has structure, panels, latticework, voids, we may detect symmetrical shadowing inconsistent with natural geology. And if there's nothing, if it shifts course before the transit, or vanishes behind solar noise, that will be data too, because a refusal to transit might suggest avoidance. 3. Historical context. Historically, transits have played massive roles in science. The transit of Venus in the 18th century helped astronomers calculate the distance between Earth and the Sun. The 2012 and 2004 Venus transits sparked public fascination and gave us the tools to improve solar imaging systems. But we've never witnessed a non-planetary transit that wasn't artificial. The International Space Station transits the Sun regularly, but it's planned, predicted, and human. With 3i Atlas, there is no launch record, no propulsion logs, no telemetry. If it crosses the Sun, we will be watching something that likely formed or was designed outside our solar system, and if it broadcasts while transiting, we may be watching more than light curves. 4. The shadow path. There's another reason the transit matters: location. If the object crosses the Sun as seen from Earth, it will cast a narrow shadow track over our surface. This is the region where ground-based telescopes can attempt to photograph or measure the silhouette. Early predictions suggest this track will pass over the Pacific Ocean, potentially visible from observatories in Hawaii, Chile, and parts of Southeast Asia. Agencies like NASA, ESA, and even private space firms are already preparing adaptive optics and polarimetry tools to capture every second. Because whether 3i Atlas is artificial or not, this transit may be our best chance to see its shape, to study its surface, to catch a glimpse of design or chaos, and if it deviates, then the question becomes, was it ever going to transit at all, or did it want us to think so? As November nears its close, and 3i Atlas settles into a holding pattern near Earth's orbital plane, a new kind of tension is spreading through the scientific community. Not because of a sudden signal, not because of an unexpected shift in trajectory, but because of something far more unsettling: silence. For weeks now, the object has maintained its position with unusual consistency. No outbursts, no course changes, no thermal anomalies, and most striking of all, no repeat of the 1.44 GHz pulse that startled deep space radio arrays just days after Perihelion. This is not how comets behave, but it's also not how probes behave, at least not the ones we build, and that silence is causing concern. Let's explore why. 1. Post-perihelion expectations. When an object like 3i Atlas rounds the Sun, astronomers expect behavior that follows known thermal dynamics. Comets typically lose mass rapidly, shedding dust, ice, and gas in plumes that push them into erratic spin states. They grow tails, change brightness, and sometimes even disintegrate, but Atlas defied those patterns, Instead of losing cohesion, it became more stable. Its coma thickened, then stabilized. Its albedo, its reflective surface brightness, peaked and then plateaued. Since then, it has coasted along a nearly circular heliocentric path, as if conserving energy, or waiting. And that waiting, that stillness, has astronomers whispering a question they never expected to ask aloud. Is it observing us? 2. The behavioral cliff. In intelligence analysis, whether biological, military, or artificial, there's a concept known as a behavioral cliff. It refers to a sharp, sudden drop in activity following a critical event. For Atlas, that cliff appears to be perihelion. Before it, activity, brightening, emission spikes, radio pulses. After it, silence, stillness, no anomalies. This kind of binary behavior is patterned. It suggests internal states, trigger thresholds, which means it may be reacting to something. But what? Some scientists believe it's responding to the solar environment. Others wonder if Earth itself is the stimulus. Because as the calendar moves closer to December, Atlas's relative distance to Earth is shrinking. Not rapidly, but steadily. It's not on a collision course, but it's tracking us, and for now, not speaking. 3. December 15th. A quiet clock. Why does December matter? Because orbital models show that on December 15th, 3I Atlas will reach a nodal point, the moment when its orbital path intersects the Earth-Sun line at the same inclination. This doesn't mean impact, but it does mean optimal geometry for line-of-sight communication. In simple terms, if there was ever a day to send or receive a signal, it's that day. Think of it like the alignment needed for laser comms or interplanetary telemetry. Clean paths, minimal interference, and perhaps anticipation. Because some theorists believe this silence isn't passive, it's preparatory. Just like a spacecraft enters safe mode before critical maneuvers, or a satellite goes dark before reorienting. 3I Atlas may be entering a pre-execution state. That's speculation, of course, but silence, in this context, is not nothing. It's data, and that data is unsettlingly consistent. 4. The global listening effort. Right now, radio telescopes from 5 continents are listening, not just for that 1.44 GHz signal, but for anything: pings, bursts, polarization anomalies, even reflected transmissions, but the skies remain quiet. And while some interpret that as proof of randomness, others interpret it as something worse: deliberate silence. Because sometimes, the absence of a message is the message, and in the countdown to December 15th, that silence has become its own kind of noise. A pause, a breath, a shadow cast across the confidence of modern astronomy. We're listening, and whatever it is, it's waiting. So much of science is built on light, measuring it, chasing it, interpreting its silence. But tonight, it's the stillness that matters. Because as 3I Atlas drifts silently across the orbital threshold, as observatories tighten their focus and transmission logs go blank, one thing has become clear: this isn't just a comet anymore. It's a mirror to our assumptions, to our models, to the way we process the unknown, and whatever happens on December 15th, signal or no signal, movement or silence, we'll be watching.